Okay, so in this online lecture I'm going to be talking about the sort of practical application of the temperature and entropy phenomena that we've talked about already in paramagnetic systems. Okay, so the practical application is actually in a type of fancy refrigeration. So there's something called an adiabatic demagnetization refrigerator, an ADR, that's used to reach very low temperatures. So I'm going to start out by just describing empirically how these systems work, how these ADR refrigerator systems work, and then we'll try to get some understanding of how it's working by considering the two-state paramagnetic system. Okay, so this topic is about the adiabatic demagnetization refrigerator. Okay, so let's just start out with one or two empirical facts. Okay, so these are sort of, you could take these as experimental observations. So one experimental fact is that if you have a paramagnet that's in a magnetic field and you suddenly increase the strength of the magnetic field, then the paramagnetic material, now we're talking about real physical paramagnetic material here, rather than some idealized just the two-state system. So the real material heats up, it gets warmer. So that is, if you increase the B field, then the paramagnetic material, let's say, just to emphasize that we're talking about real material here, heats up. It gets hot. So that's observation number one. And the opposite is also true. That is, if you have a paramagnet and it's sitting in a magnetic field and you suddenly decrease the strength of the magnetic field, it cools off. So the opposite here is also true. So decrease the B field and the magnet gets cold. So cools down. So this observation by itself is enough to sort of understand the basic steps of how this ADR refrigerator works. So let's call this ADR. So how does ADR work? So ADR, the refrigeration process follows a few steps. So let's write them down. So step one. Step one is to take a paramagnetic material and increase the magnetic field. So we increase B while the material is in thermal contact with some heat sink. Okay, so keeping it at fixed temperature. So while the material is in thermal contact with a heat sink. And that's so basically keeping the material at fixed temperature. So by keeping it at fixed temperature, if you did not have it in contact with the heat sink, it would heat up, right? That's what we're talking about here. So, but the first step of this ADR is to increase B while the material is in contact with the heat sink. So this material is dumping heat into the heat sink as we increase the magnetic field so that it remains at a fixed temperature. Okay, so then step two. Step two is to detach the heat sink. So you take it out of thermal contact with the heat sink. And then you turn the field down, so you decrease the B field. So it's not in contact with the heat sink, so it can't remain at fixed temperature. If we decrease B, the material is going to get cold. So this says the material gets cold. And then finally, you take this cold bit of paramagnetic material and put it in contact with whatever it is that you would like to cool off, right? So now put material in contact with what you want to cool. So that's the step where the paramagnetic now absorbs heat from some other system and cools the other system off. And then you repeat this process many times, and this type of refrigeration is often used in scientific experiments where you need to reach very low temperatures. So this type of refrigeration can get down to you can get down to temperatures as low as millikelvin. So this can give you down to 0.01 Kelvin. So you're talking about very, very low temperatures that can be reached by this type of refrigeration system. Okay, so now what we're going to do next is take a bit of time to try to understand how this works in each of these steps. And we're going to do this in thinking about the two-state paramagnetic system. Okay, so remember these steps because I'm going to be referring back to them. So step 1 is increasing the B fields. Step 3 is the decrease in the B field. So let's erase this. And to understand what's happening here, we're going to do a little bit of thinking about energy in these paramagnetic systems. So recall that the total energy of these systems is mu b n minus 2n up. So that's the total energy of the paramagnetic system. Now, also recall that the magnetization, so there's a very similar, it almost looks like the same formula, but it's not quite the same. The magnetization of the paramagnet, that is the excess magnetic field created by the alignment of the dipoles in the paramagnet, is it's almost the same. It is mu n minus 2 n up with a minus sign here. So this is saying that U is equal to, or minus U over B is equal to M. So this is the magnetization, this is the total energy. Okay, so now if we consider a small change in energy, that is going to be equal to, well, now in the past we considered a small change in energy where B was fixed, but here we're going to allow this energy to change due to some change in B as well as some change in the number of up-pointing dipoles. Okay, so if we're going to consider a change in U due to possible changes in B and N up, keeping big N fixed, then this can be written as follows. So you can kind of do a product rule on this. You get a sort of mu dB, and then we consider the change in the other part of the system, so we get a minus 2 mu b d n up. Right, n is fixed. So the second term comes from considering the change in this term, which is only due to the change in n up. Okay, so we can rewrite this slightly. This is, again, using this definition of the magnetization here. We have minus m dB. So that's replacing this mu times n minus 2n up with an m, and then we have this 2 mu b dn up. Okay, now I'm going to do a little bit more manipulation to see what this term means. Okay, so it's related to temperature. All right, so if you recall that our temperature is ds du to the minus 1, and if you look at the relationship between u and n up, then we can replace this with 1 over minus 2 mu b ds dn up. This is all to the inverse, or to the minus 1 power. Okay, so now what we can see is that all right, so let's rewrite this one more time here. We've got then I'm going to go ahead and invert it, take care of this minus 1. So we have a minus 2 mu b dn up ds, or considering, I'm sort of rewriting this considering small changes rather than these partial derivatives. So ds, and now we can see then that T ds, so some small change in entropy, and putting this ds on the left-hand side of the equation, is this minus 2 mu b dn up, right? It's this term. Therefore, we can now say that a small change in energy for this paramagnet is minus magnetization times some small change in B, and then we have this term, which is plus T ds. And what we've got here, and what we're going to use this eventually to understand the ADR. What we've got here is basically like a thermodynamic identity for the two-state system. Okay, so that's what I wanted to get from considering energy here. All right. Now, okay, so but maybe before I move on too much now, I want to point out that this is sort of an aside here. This is sort of an E&M, or electricity and magnetism aside here. So it turns out that this mu dB, or this m dB term, is closely related to magnetic work done in a system. So let's write this down here. So I'm going to use this. So the work, you can calculate the work required to make a change in magnetic field for a particular magnetization. So this thing could change as you do this integral, but so big M could depend on the magnetic field. To doing this integral is not always simple, but this is the work, it's the magnetic work required to change the magnetic field. So work required to change the B field. And literally, if you're thinking about this in physical terms, changing a magnetic field, if you're creating this magnetic field with a giant magnet, electromagnet of some kind, then if you increase the magnetic field, you have to run more current through your coils, and that electrical power is related, that change is related to work that's required to change the magnetic field. Okay, so this aside, then what we're looking at here is a sort of some work done, and this is related. Well, okay, so let's just keep that in mind for a moment. And what we're going to consider next is the first law of thermodynamics. So if we go back to the first law of thermodynamics, which is just that. Okay, so first law of thermodynamics states that a change in energy of a system, remember, is the heat added to or removed from a system plus the work done on the system. Now, this work done, in the case of the two-state paramagnet, must also account for this magnetic work. In fact, that is the only work that's being done on the system as we're changing magnetic fields in the problem that we're considering right now. So in our problem right now, this is Q minus this integral of m dB. Right? So in the steps of this adiabatic, in the steps of the ADR refrigeration, which involve fixed magnetic field, that's the situation where this work is 0, right? dB is not changing. So in any step where the work is 0, or the magnetic field is not changing, which is for instance, that's the step where you put the cold material in contact with the this thing that you would like to cool while the magnetic field is fixed. In that case, this term is 0, and the change in energy of the system is just well, let's finish thinking about this. So if you take your thermodynamic identity here and you relate it to this expression, so if you take this expression and you integrate it, so integrate this, then you get an integral of du equals this minus integral of m dB plus the integral of t ds. Right? And this left-hand side here is delta U. That's a change in energy. This term is the work done, and that means that this term must be the heat. Right? This term must be the heat. So, all right. So then we're left with this situation where this Q is equal to TdS, right? And for the step where we put in contact, okay, so for step 3, okay, so let's consider the step 3 of the ADR process. Step 3 is the step where we turn the field down slowly and the system is getting colder. So that's the step where, let's see, maybe I'm going to revert to some drawings here, but okay, so for step 3, right, that's the part where we're decreasing B and the paramagnet is getting cold. So in that situation, the system is not in thermal contact with anything else, so there's no heat exchange. So step 3 has Q equals 0, and the energy change of the system is all directly related to the magnetic work that we're doing. So this is the case. Now for step 4 of the process, let's see here, and maybe I'll go back and do step 1 and step 2 here in a moment. Okay, so for step 4 of the process, we're putting the system in thermal contact with the thing we want to cool off while the B field is fixed. In that case, the delta U is equal to the heat that's lost or gained from the thing we're cooling off, and WB is equal to 0. Now, what's happening in the other steps? Well, step 2 was just removing it from the heatsink. Nothing happens there. Step 1 was the step where we increase the B field while the system is in thermal contact with the heatsink. So in that case, we have both Q and W going on. So just to keep everything, keep track of everything. In step 1, both Q is non-zero and W is non-zero, but the delta U is 0 because we're keeping the temperature fixed, right? We keep temperature fixed, so there's no change in energy, so Q is equal to minus W. So all the energy that we're that we are dumping in by doing magnetic work is being dumped out into the heat sink directly. Okay, so that's just some of the tools we need to understand what's happening here. Okay, but I was going to make a point about step where we give up the temperature. Okay, so that's this step. Okay, so what I just erased, remember, was the relationship that said that Q in this system, Q is equal to the integral of T ds. So you can look at your paper. What I just erased said that. And what's happening in step 3 here is that Q is 0. So if this is 0, even though, let's see. In step 3 is the part, no, I'm getting confused here. So this is in step 4. Okay, well, never mind that for just a moment. Okay, let's go back to what I want to do now is draw some diagrams of how entropy, so what's happening in this process if we think about entropy and energy. So here's energy, and remember, if we consider the entropy and how it depends on energy in these two-state systems, it's this sort of hump curve here where at the highest we have a plus mu b n, and here we have a minus mu b n. Now this would be for one value of the magnetic field, let's say b1. But if we change the magnetic field, if we increase the magnetic field to some higher magnetic field, then the new entropy versus energy curve is something like this. So that would be, so this is for B1 and this is for B2. So this has got a different extreme value that's allowed, right? If you have a higher magnetic field here, it can get up to mu B2n. Okay, so these are the two possible curves for two different magnetic fields for the entropy versus the energy relationship. Now, similarly, we could consider the temperature versus energy for these two different situations. And so for one case, well, for both cases, you get this weird infinite temperature at 0 energy, right? But there's two different curves here for the two different magnetic fields that could be applied. So this is the B2 case is the one that's at higher temperatures, and the B1 case is at lower temperatures. Okay, now one more thing to consider that we haven't looked at previously is, all right, so let me draw this over here. So we'll draw the entropy as a function of temperature. Okay, so if we consider entropy and how that changes with temperature, it's sort of implicit in these two curves, right? S depends on U, T depends on U. So how does S depend on T? That's what we're going to draw here. So this curve has a shape that's sort of sigmoidal like this, and this would be for the lower. This is the lower magnetic field, and this is for the higher magnetic field. Right? For a fixed value of entropy, the lower magnetic field has lower temperature than the higher magnetic field. Okay, so where does the ADR process go along these? So that's what we're going to consider. We're going to try to draw a path on this curve, or on this plot, to describe what happens during the ADR process. Okay, so let's say initially we're sitting at one magnetic field level, and in step 1, remember, what we're doing is increasing the B field while maintaining constant temperature. So we increase from magnetic field 1 to magnetic field 2 while maintaining constant T, right? That's a vertical line on this plot. So this is step 1. We increased the magnetic field and entropy decreased. So maybe we can draw that on this curve over here too. We start at B1 somewhere, and we go to some lower, it's got to have the same slope because we're talking about the same temperature, but it's going to a different magnetic field at lower entropy. So step 1 is right here. And similarly here, if we draw a point, so step 1 is here. Fixed temperature, changing the energy. Okay, so now what happens? So step 2, I guess that's sitting right here. We detach from the heat sink. So step 3, where does step 3 go on this chart? Okay, so step 3 is when Q is equal to 0. So that's the step where we turn down the field again. So we're going back from B1 down to B2, and we're doing it in such a way that there's no heat exchange with the environment. Remember, we're detached from the heat sink, so there can be no heat exchange, just Q equals 0. And what I was going to point out earlier is that what we show is that TdS, from considering that sort of thermodynamic identity for this magnetic system, we can show that the Q is related to TdS. So if Q is equal to 0 and temperature is changing, then ds must be 0. Right? So if Q equals 0 and T changes, then this expression implies that entropy is fixed. ds equals 0, so entropy is fixed. So this line for step 3 in the process is isentropic, that is at fixed entropy. So this is step 3. And then finally, as you put the system in contact with the thing you'd like to cool off, and it warms back up again to some temperature at fixed magnetic field, it goes back along this line for step 4. So you get back to here, say, as you heat up to the temperature of the thing you're trying to cool off. And then once you do that, you can repeat this process many times. So what happens if you repeat? So now you're at this temperature, you change the magnetic field again, you go to there, to here, you heat up again a little bit, you go there, and there you go. You're progressing downward in temperature as you keep repeating this process over and over again. The refrigeration goes to a lower and lower temperature as you repeat the cycle. Okay, so that's a rough version of how this adiabatic magnetic refrigeration works.